All right, so this is Math 466, Advanced Applied Analysis, Lecture 27. We're finishing up the classical Wigner semicircle part, and we were down to an integral. So we wanted, I think, I2m was the integral, so hopefully somebody can remind me, was this 0 to pi halves? We were doing things in terms of trig, 0 to pi halves, and we had, was it sine to the 2m minus 2 cosine? Oh, no, sine 2m cosine. It was 2m, I think, of u cosine squared of u du. Right, this is what we had, right? And then we defined, I think, j2m to be the integral from 0 to pi halves of sine to the 2m plus 2 of u du. And then we got a recurrence relation, j2m plus 2 was equal to 2m plus 1 over 2m plus 2 j of 2m. Okay, good. So did I have something slightly wrong?
I think we had a coefficient of 2 in front of this integral.
Oh, in front of this one?
I think in front of both.
Okay, could be. Okay, so this is what we had? Okay, excellent. And so if we want, we can then just keep going by induction. So, j of 2m would be 2m minus 1 over 2m, j of 2m minus 2. So this would then be 2m minus 1 over 2m, 2m minus 3 over 2m minus 2, j 2m minus 4. And we keep doing this all the way down. And so how far should we go down to? So we'll go, 2m minus 1, I think, double factorial over 2m double factorial. And we would stop with, I think, a j of 0. So this is always, we have to be careful as to how far do you go. So we want to keep going all the way down until we have a j of 0. Well, what would it mean for j of 0? That would mean an integral of sine squared. Okay, well.
1 over 2m.
I'm sorry?
Oh, never mind.
Okay.
Wrong cancellation.
Okay, so let's think. So what would j of 0 be? That would be integrating sine squared from 0 to pi halves. That's the same as 1/2 the integral of sine squared plus cosine squared from 0 to pi halves. So it would be 1/2 times pi halves times 2. So I think it should be pi halves. So I think it should be like 2m minus 1 double factorial over 2m double factorial. We may have the constants slightly off, but it should be something like that. Okay. So when we look at the double factorials, this looks a lot like binomial coefficients. So there is a very high chance that we will be off by one small factor, which will be a little bit annoying, but so be it. What would you love to do to a double factorial?
Cancel copies.
So how do you reduce it?
Can we, well, I want to expand it to the full factorial. And then
So it'd be nice to expand it to the full factorial. So we have 2m minus 1 double factorial over 2m double factorial. This wants the odds. So let's put the odds in. 2m minus 1 double factorial, 2m minus 1 double factorial. And so now we have 2m minus 1 double factorial squared over 2m factorial.
Yeah.
So this is beginning to look like a binomial coefficient. What would we want up top? So we've got all the odds up top. So I would want to put in, I think, 2m double factorial squared.
Yeah.
And then I would have to divide by 2m double factorial squared. And now the top becomes a 2m factorial squared. We have a 2m factorial down below, so we're left with a 2m factorial above. Down below, we have 2m double factorial squared. That's the same as 2 to the m factorial, 2 to the m factorial. So that's going to be a 1 over 2 to the 2m choose m. Because 2m double factorial, it's the evens. I pull out a 2 from each term. And so since I'm pulling out a 2 from each term, I get a 2 to the m and then an m factorial. So when we're looking at this, we see that there is the binomial coefficient 2m choose m.
Wow.
Now, I think we were supposed to have like a 1 over 2m plus 1 for the Catalan numbers.
Yeah.
So the question is, did we miss one little piece? No, there's also the pi over 2. Now that's going to come from the normalization constant. We have a 1 over pi over 2, which will cancel with that. I'm not worried about that part. So the question is, did we shift something somewhere by just a little bit? And so it looks like we dropped a factor in one place. We can go back and we can chase it down. I'm not particularly excited about chasing it down.
Sorry, what is it supposed to be?
Well, we're supposed to get the Catalan numbers, and the Catalan number should have a 1 over m plus 1. So a 1 over m plus 1 is really like a 2m plus 2. And so
So roughly like 1 over 4.
Not 1 over 4. But we should have an m factor. So the question is, we want to get I at the end of the day. This is j. So how is j related to I? Right. We had some relationship between I and j. So does anybody have that from last time? Otherwise, we'll have to integrate by. Okay.
I of 2m equals j of 2m plus 2 divided by 2m plus 1.
Divided by.
2m plus 1.
Ah, good. And there's the 2m plus 1 that we're missing, because this is j. We need I.
Nice.
So j of 2m would equal this. Now we would also have a pi over 2. So now this was j of 2m plus 2, I think. Or this might have been. I'm sorry.
I think it's just 2m.
I think this is j of 2m. So now we might have the indices slightly off. I don't really care about that. So I of 2m is roughly going to be pi halves 1 over 2 to the 2m, 1 over 2m plus 1, 2m choose m, something like that. My index may be off by 1. I'm not really that concerned. But we were calculating the j's. We wanted the i's. There was this nice relationship between the i's and j's, which we got integrating by parts. The 2 to the 2m is just coming from how we're normalizing things. We want to go from -1 to 1. This is why we divide by 2 square roots of n. The pi halves, that's the area. We're supposed to remember our probability distribution should be a square root of 1 minus x squared divided by pi halves. And we did 3 different ways of getting that. So the pi halves is going to vanish. The 1 over 2 to the 2m, that's going to be just because we want to look at -1, 1. And here's the Catalan number. So the rest is just small bookkeeping. But we're at the point where we actually see the binomial coefficient emerge. We then see the extra factor which we need for the Catalan contribution. So what's remarkable about the space of real symmetric matrices is every configuration either contributes fully or doesn't contribute at all. Which ones contribute fully? The ones that don't have any crossings. And the number of such as Catalan, there is a nice formula for that. It's a recursion. It's a more involved recursion than the Fibonacci's. But we were able to solve that using generating functions. The crossings, we did a degree of freedom argument. And one of my advisors calls this counting on your fingers. And you want to just get order of magnitude estimates and say, look, worst case scenario, how much could this contribute? Oh, it contributes at most 1 over n, and n goes to infinity. Or it contributes at most 1 over square root of n, and n goes to infinity. It's negligible. If you care about how quickly things converge, then it matters. How many of you have taken a statistics class? All right, how many data points do I need? How many is a lot? If I want to feel comfortable using the central limit theorem, for instance. Well, typically they say, I think you want to have at least this many points if you want to use the central limit theorem. I thought it was around 30. That, around 30 data points, you should be pretty comfortable. How comfortable is pretty comfortable? If you're doing surveys, you want to have about 2,000 people in your survey so that your percent error, I think, is reasonable. It's how many percent do you want to be within? And so you have a lot of these questions where the actual answer is going to depend on the distribution. And the more complicated the distribution is, the more pathological it is, the more data points you might need to really see what's going on. But let's assume it's normal, and if we assume it's normal, by the time we hit this amount, we're fine. You might also see this for t-tests. At what point do you stop doing a t-test and say, hey, it's approximately a normal, let's just do it that way? So there are times when you want to know how close am I? And then you would want to calculate the lower order terms. Okay, so this is a good place to end the unit on Wigner's semicircle law. So this gives us density of states. And again, what I like about this is there's a lot of really good tools and techniques in this. As an aside, the question is, can you think of any other ways to calculate these integrals? How could you compute these integrals? One way you might be able to do it, and it would almost surely be much worse, is let's integrate maybe cosine to a power or sine to a power, and we have these angle duplication formulas. We had cosine of 2u in terms of stuff like that. Maybe we replaced cosine squareds with something like that, expand it out, and and keep playing games like that, and try to reduce it. The other thing is, we did Fourier analysis, right? Yes, we did Fourier analysis in the beginning. Give me a really good theorem from Fourier analysis. I give you a continuous periodic function. Give me a good theorem. I'm sorry? Fay's theorem. But if my functions say continuous and differentiable and twice differentiable, rather than using Fay's theorem, I could use Dirichlet. Right? Sine to the 2m, let's just do sine 2mu. According to Dirichlet, this should be a sum of f hat of n e to the 2 pi I nx. Well, so here, I'll change things here, and I'll put in a 2 pi over here. Right?
Why do you put the 2 pi in?
Well, because when we're doing things with the Fourier series, we always did things that were periodic on 0, 1. So rather than looking at sine of u, I'm going to look at sine of 2 pi u.
Yeah.
So change of variable, not a big deal. This is tactical nuclear strike, overkill. By Dirichlet's theorem, we can expand sine like this.
Yeah.
All right, what can you tell me about f hat? F hat of n versus f hat of minus n. Do you think the Fourier coefficients are even, odd, or mixed? So we would want to look at the sine to the 2m 2 pi u times cosine 2 pi nx plus I sine 2 pi nx. dx. Integral from 0 to 1, this is f hat of n. What's the integral of sine to the 2m times cosine? Well, if you want, integrate this from minus a half to a half. It's periodic. What's the integral of sine to the 2m times cosine? It's an integral you should be able to do in your head. We're integrating it from minus a half to a half. What's the value?
0.
0. Why is it 0? Cosine is even, sine is odd.
Yeah.
So sine times cosine is an odd function. We integrate over a symmetric region. It's 0. Sine times sine is odd.
Yeah.
And so if I replace n with negative n, all that happens is this plus becomes a minus. So f hat of n will equal negative f hat of minus n. So this is actually going to give us some information about the Fourier coefficients. So this will be the same as the sum n goes from 0 to infinity f hat of n, and now we'll have e to the 2 pi I n x minus e to the negative 2 pi I n x. And I'm not going to take n equals 0. I'm going to take n goes from 1. The reason is if I take n equals 0, I get 0. Remember, we've got to be careful. If n equals 0, we can't say the integral against cosine. Oh, wait a minute. Wait, we have sine to the 2m. Sine to the 2m is not odd. Sine to the 2m is even. We have it to an even power. Okay, so rewind. All right. We go back here. Because we have this to an even power, the sine times the cosine contributes. The sine times the sine does not contribute. So f hat of n equals f hat of minus n.
Yeah.
So now we just come over here, and because they're equal, it's like this. All right. Small change. Well, now when we look at this, this is going to be cosine plus I sine. This will be cosine minus I sine. So the sines vanish, the cosines get doubled, and this will be the same as twice the sum n goes from 0 to infinity of f hat of n cosine 2 pi n x. This is probably the longest overkill way to find the expansion of cosine, or sine to the 2m in terms of just sines and cosines. But if you think about it, we can write any nice function, any periodic differentiable function in terms of sines and cosines. Because the function is even, we don't need any sines, so we should just need some cosines. So all we have to do now is calculate these f hat of n's, and then plug them in here. Is it hard to calculate f hat of n? No, this is actually essentially what we want. Right? We want to integrate a sine times a cosine. What's the only problem?
The variable.
The variable.
Can we pull the sign out? It's 2 pi u. We're just integrating cos. Never mind.
So unfortunately, this is not.
It's not the antiderivative.
It's not.
Right.
So that integral is work. So then the question becomes, is there an easy way to figure out what that integral is? And so at this point, I'm not seeing a really good way to do this. But we do know that there has to be some kind of expansion like this. There are games you can play where you can keep expanding signs out. You can keep using angle formulas, angle identities. If you got something like this, then it would be very easy to find the integral. You would just integrate term by term. So it's good to just get a sense of what are the different ways you can attack a problem, which ones work, which ones don't. We did prove all these great theorems in Fourier analysis. Can we use them? Well, we can use them if we can calculate f hat of n. We have this extra factor of n over here. How do we deal with this? Oh, and if this is I guess I should be writing x over here. So sadly, there is.
We can toss the I sign, right?
We can toss the I sign. So this part over here will be 0. We can definitely toss that.
Pull the sign of the 2n up front, right? And we're integrating cosine 2 pi n.
No, because this has x dependence.
Oh, sorry. Yeah,
Right. I had written u by mistake. It should be x because I'm writing it now like this. And so unfortunately, there's no way to balance this. And so this is just now a painful integral to do. And so is there a way to do this? I don't know. Okay, so this finishes the stuff I want to say on Wigner's semicircle law. The next question is, we know the density of eigenvalues. We know how many eigenvalues do you have in a given regime. What is the spacing between eigenvalues? So this is now going to be our goal for the next few days. And I only want to do 2 cases today. So I need to look at n by n matrices. What is the first case I should study? What size matrices? Yes, no. You're the second case. And I do appreciate which finger you chose to raise. Okay. He did not raise an inappropriate finger. How many of you know the song Where is Thumpkin? Here he is, here he is.
I don't have children.
Years ago, they taught my children Where is Thumpkin at the youth center. And they did all the fingers. So they eventually got to Where is middle finger? Here he is. Here he. It was a South Park moment that I was not expecting, but I came in to get them that day. Let's look at 1 by 1 matrices. I choose the main diagonal and everything above, if any.
I can calculate the eigenvalues pretty quickly.
Excellent. So we have A11. And can you calculate the eigenvalue for me? A11. Amazing. Spectacular. So what is the distribution of the eigenvalues? I'm sorry? But now as I vary the A11s, as I look over all my matrices, what's the distribution of lambda 1, 1?
The same as your distribution.
The same as A11. So the distribution of lambda 1 is the same as the distribution of A11. So whatever we're choosing the density for the A11, that's the same as the density of the eigenvalues. There is really not much to do in the 1 by 1 case. And we want to understand what's going on as n goes to infinity. So again, the motivation for this was trying to understand heavy nuclei such as uranium, where you have over 200 protons and neutrons in a very complicated interaction. All right, building on the remarkable success of 1 by 1 matrices, what should we do next? 2 by 2. What did you want to do? Move on. Right. We are not going to look at fractionally sized matrices. We'll go up to 2 by 2 matrices.
Are those defined fractionally by matrices?
I'm sure that someone has defined it. Yes. I mean, we have fractional derivatives which occur in some things in economics. We have fractional integrals. I just got a paper for the Journal of Number Theory, which was a new type of irrational number. And they said, well, I actually don't have symbols for this, so I just took a picture of my handwriting.
Why is that necessary?
It's not. And yes, I know this is being recorded. A11, A12.
So what's the journal's official stance on
That will not be said while this is recording. But of course, we give all papers the consideration they deserve. Anybody ever seen Hitchcock's The Rope? Somebody's introduced, oh, so-and-so has said so much about me. I hope they did me justice. Do you deserve it? So here's our matrix. It's real symmetric, so I've written A1, 2 over here. I want to calculate the eigenvalues. How do we find the eigenvalues?
Characteristic polynomial.
Yeah, we could actually do this by brute force. Determinant of A minus lambda I equals 0. So we get A11 minus lambda 1, or minus lambda, A22 minus lambda minus A12 squared equals 0. Now what do we do? So it's a little bit harder than the 1 by 1 case. What do we do now? Yeah, just use the quadratic formula. So now if we multiply things out, we get lambda squared minus A11 plus A22 lambda plus A11 A22 minus A12 squared equals 0. This so you actually have a nice expression for the polynomial. That's the trace. This is the determinant. As you get to a higher and higher size matrix, you will still have something like this. The first term will always be the trace, lambda to the n minus 1. The last term will always be plus or minus the determinant. And then you have other terms in between. So now we get lambda equals what? So negative b, so it's going to be the trace of a plus or minus the square root of b squared, so the trace of a, minus 4 times the determinant of a, all over,
Not trace squared.
sorry, thank you. Trace squared, thank you, all over 2. Or being explicit, now lambda is the trace of a, which is a11 plus a12, plus or minus the square root of a11 plus a12 squared minus 4 a11 a22 minus a12 squared. All right, so we're smelling cancellation. That'd be nice.
Not a lot.
Well, let's think. We have a minus 4 a11 a12. A22. We have a minus a12 squared. So let's say, the trace is a22. So this would be a22. So here,
Outside as well, right?
and outside as well. All right. So if we look at what's going on here, this is a11 squared plus twice a11 a22 plus a22 squared minus 4 a11 a22. So that becomes a11 minus a22 squared.
Yeah.
So we are getting some cancellation. So we get lambda is a11 plus a22 plus the square root of a11 minus a22 squared. Minus and a minus is a plus 4 a12 squared all over 2.
Dropping the minus.
Dropping the minus.
Okay.
Thank you. All right. We know what A11 and A12 and A22 are drawn from. So half the class has taken probability with me. They're independent, identically distributed random variables.
In different places?
I'm sorry?
Should we start sitting in different places?
No. It's really convenient.
Yeah, people wearing great bread.
There are certain reasons why it's nice. I can just say, this side has taken probability. So as an exercise for them,
I've taken probability.
you went in my class. So I don't know what you've done because It was not a Miller-sanctioned class.
They probably used the Miller book, right?
No. These were the Europeans, right?
Oh, you did over
Yeah,
there.
they're over there. Do you want to calculate what this distribution is? I mean, we now have something about this.
It's a non-linear transformation, right? How would you do that? Like if it's a linear transformation, then you can figure out the distribution.
So this is an exercise. I want to calculate, for instance, what's the probability that this lands in a given area. So if I specify A11, A22, then I would have a range for A12 so that certain things would take place. So if I want to calculate, what is the probability that, say, lambda lies in an interval, say, alpha, beta, or maybe alpha plus delta, or maybe plus some small amount epsilon. I would then have an integral A11 goes from minus infinity to infinity, an integral A22 goes from minus infinity to infinity, and then I would have to figure out what's the range for A12. And then the question is, would there always be a range for A12? Or sometimes would there not be a range? But we could do something like that. Well, if I know what A11 and A12 are, I know what this quantity is. I know what this quantity is. I would then have to figure out what, this is a positive square, so maybe there won't be anything that would work. So for instance, maybe I want this to be a value 7. And this is already 1,000, and that's already 1,000. Well, but maybe then I could subtract enough.
Yeah.
So then you can go and you can figure out what would be the ranges of A12. And then you would have, the range, you would have P A11, P A12, P A22, DA12, DA22, DA11. So I will leave this as an exercise. If this was a homework problem, this is where you say it's not worth it. I had one homework problem like that when I was an undergraduate. It was, there's a beautiful result in complex analysis. If you have any simply connected domain that's not the entire complex plane, there is an infinitely differentiable conformal map between that and the unit disk. And we were told to explicitly calculate what this was for, like, the pentagram. I'm sorry? Explicitly. Yeah. It was the one math physics problem in my career that I just said it's just not worth doing. I took the 10-point hit. It just was not worth doing. It wasn't worth doing the calculation. I'll leave that as an exercise for you to do. What do we do after 2 by 2 matrices? 3 by 3. So now we go through and we do this 3 by 3. If you thought this was pleasant, okay, you obviously need help, but if you thought that this was doable, you can imagine what it would be like for 3 by 3.
Throw in the towel again.
Building on our success, now what do we do? After our success with 3 by 3? No. 4 by 4. We do the 4 by 4. We go through. And now at this point we're getting a little bit concerned, but we still brave forward and we do the calculation. Now what do we do?
Now we give up.
What should we do after 4 by 4?
Twice in a row.
What should we do after 4 by 4? And are we able to do the argument the same way for 5 by 5?
Is it 3 strokes you're out now?
No. What breaks down? If something breaks down at 5 by 5. I'm not just trying to fill up class time.
Is there no closed form solution?
There is no closed form solution for the roots of a polynomial of degree 5 and higher.
Let's go.
Right? This is Abel's theorem, or you see this in Galois theory, that if I give you a polynomial of degree n, and roots, that's the fundamental theorem of algebra, how do you find them? Well, we have numerical methods we can use to find them. I think we did Newton's method, either in this class in operations research. We do divide and conquer. We have ways to find them. But to write them down in explicit form, we don't always have that. This method crucially uses the idea that we are calculating the eigenvalues by solving a characteristic polynomial with explicit coefficients in terms of the polynomials. And that gives us a formula for the eigenvalues in terms of the matrix coefficients. This breaks down at 5 by 5. So even if this hadn't deterred you, and if doing the 3 by 3 and the 4 by 4 case hadn't deterred you, at this point, fortunately, mathematics saves you from having to calculate something even worse. Because even if you wanted to continue doing this, and you shouldn't want to, you can't, because you can't get here. So it means we need a fundamentally new way of attacking the problem. That what we're doing here is not enough. So again, this goes back to trying to find the limits of techniques. Oftentimes, you can do small cases using one set of methods, but those methods will not always generalize. And that's the problem we're running into here. That the 1 by 1 case was, so easy. The 2 by 2 case, it's not horrible, but there's work to be done. You can at least say something about the average values of the eigenvalues. If I want to look at the average values of the eigenvalues for a 2 by 2 case, what can you tell me on average?
Shouldn't be A11 plus A22 divided by 2.
Okay, and what is that on average?
Is it uniform distribution?
Nope. But what are we assuming about our probability distribution? We're always assuming our entries are chosen from what kind of distribution? I'm sorry? We're not assuming normal. But to do all the moment calculations, we assumed something about the distribution. I'm sorry? Infinite moments? Finite moments. All the moments are finite, but more than just finite. More than just finite. What else do we assume about the moments? What values do we assume for the... The mean is 0, the variance is 1. So what's the mean of A11? The mean of A22. And because they're independent, actually we don't even need independence, the expected value of a sum is the sum of the expected values. The mean is 0. So we can at least easily see in this case that the mean is 0. We might even be able to talk about something about spacings between eigenvalues. Imagine I only want to care about the spacing between eigenvalues. Well, the spacing between eigenvalues isn't that bad. It's going to be basically double this. It's going to be basically the square root, because I've got the 2 over here doubles. So if I want to calculate the spacings between eigenvalues, it's just the square root of this. Well, rather than studying the spacing between the eigenvalues, what should I study? So the spacing between the eigenvalues is the square root of A11 minus A22 squared plus 4A12 squared. Rather than studying, study the square of the spacing between the eigenvalues. Figure out what that distribution is, and then take a square root. Do a change of variable afterwards. So if we only care about the spacings between eigenvalues, that's actually not terrible. If we care about the actual values of the eigenvalues, it's bad. Okay, so we're now at the point where we need a fundamentally new idea if we are going to find the distribution of the eigenvalues. The naive idea of just trying to calculate was wonderful, but very quickly breaks down either by painful mathematics, and if you want, look at the cubic formula, look at the quartic formula, or it breaks down in the fact that, well, once we get up to 5, we no longer have the explicit formula. So for Friday's class, we will then go, I think it's chapter 16 or 17, I'll double check my notes and email. We'll then start going through, how do we handle a problem like this? What's the new technique? What's the new method we need to look at these things to get a tractable calculation? And what's going on is we have, the number of eigenvalues is getting very, very large. It's going to infinity. How do we zero in on one of the eigenvalues and figure out what's going on? All right, there's 5 minutes left. It is not worth doing. It's not worth starting a new subject right now. So I will say this is close enough.